Okay,
Oh, good.
good.
We
Okay,
see.
let me start. So, good
Please.
day. My name is Andrii Tytarenko, and I'm here today to present a paper, Learning Visual Neural Network Policies for Caregiving Robotics, a conference paper. So, what is caregiving robotics? Well, the task of caregiving is basically means that a person, or in this case, a robot, takes care of a person who needs this care. For instance, this can be a disabled person, or a person who needs medical attention, or just an elderly. Just a lot of other examples can be here. The importance of caregiving robotics is basically due to the recent trends of first growing numbers of people who do need care, like growing life expectancy, meaning that there will be more elderly actions like war actions in Ukraine, for instance. So the importance of the task is of a paramount significance here. On this slide, you can see an example of automating this task using caregiving robots, using robotics basically. On this slide, you can see an image where a robotic arm equipped with a fork is tasked to pick up a piece of food and then bring it to a person's mouth such that it can acquire the food and, well, eat it. So one of the problems with the current state of caregiving robotics is prices and costs. So for instance, on the left, you can see a Kinova arm, robotic arm, which is 6-axis, 6 degree of freedom robotic arm. And you can see that it's kind of pricey. It costs 36,000 euros, which is super expensive for, especially for someone living in Eastern Europe or in Ukraine. But Kinova actually produces robotic arms specifically for assistive tasks for caregiving robotics. And the Stretch 3 robot in the middle that you can see is a mobile robot which can move in the space, which can just using those tiny wheels, and it's also equipped with a pretty simplistic robotic arm. It's useful for tasks such as bed bathing, where you want a robot to move from one part of a room to another part of a room, picking up certain objects and applying it for taking care of a person. And on the right, you can see a Jacko robotic arm, which is a specific arm trained to do a lot of different assistive tasks, such as feeding, for example. And it's mountable on a pretty simple electric wheelchair, as you can see on the right image. But again, you can see that it costs astonishing $50,000, which is again super much, right? So a lot. So why is that? What's the reason for for that cost? Well, the reason is that we need, and people who make those arms need to make sure that those arms are safe. And the safety comprises of three things. First is a safe and robust software, algorithms, and stuff like that, which relies on sensors, actuators being, again, fairly robust, especially if you take classical approaches with mapping, simultaneous localization and mapping, building occupancy grids, relying on some classic algorithms for grasping and manipulation. Tests and quality assurance, which is of course takes a lot of time and money and pretty qualified experts. You have to pass certain certifications, so it also takes a lot of money, and of course expensive hardware. So itself, the arm and its parts is very expensive. It requires very expensive sensors for classical algorithms to be working properly for mapping out the environment around, and it requires fairly expensive actuators, which are basically motors or brushless. Doesn't matter. The cost of the actuators is caused by the need in precise motion and precise movements. And again, this is because we use classical algorithms. So the question is like, why not just drop classical algorithms? We live in a deep learning era, and why not just learn a neural network policy? How do we do it? Well, it turns out that, of course, there are approaches which use neural network policies, and one of the such approaches is under the umbrella term called imitation learning, or in other words, often called behavioral cloning. The idea behind it is that that a person has to collect demonstrations of a task, and then a neural network is trained to regress or basically learn the outputs, the correct actions, given the state of the environment, which is again can be estimated using cameras or some more expensive sensors or some techniques for its visual localization, etc., etc. But it transforms that. It's like a functional mapping from that space to the space of actions which are then deployed on a robot and applied to the robotic arm or whatever the robot is. And the problem with this, especially in human-robot interaction, which is a human-robot interaction here, a scenario, is that someone has to teleoperate that robot to collect the demonstrations. So in order to collect the demonstrations, there has to be a human controlling the arm, collecting those demonstrations. And when you collect those demonstrations, you have to collect like dozens of them, hundreds of them, sometimes even thousands, depending on the complexity of a task. And then you can train a neural network and deploy it on a real robot. And it turns out to be working fairly well, especially in recent projects and recent humanoid robots. Maybe you're familiar with Figure Eyes robot or Optimus from Tesla, which all use imitation learning for their demos. The good thing about it is that it allows to solve complex tasks, and if it does not solve it, you could just add some more demonstrations and it will eventually solve it. The problem with this is that it's very easy to fake very good demos and like demonstrations and showcases by effectively overfitting to the environment in which this robot works. And this is a problem because the assistive robot does not work in a very stable environment, which is static. Humans can do weird things. Patients are different, so you have to be able to work in diverse environments. Another way to learn a neural network policy is to use reinforcement learning or deep reinforcement learning to be specific. The problem with this approach is that it's not simple efficient. In this sense, you have to, in order to train a modern model-free reinforcement learning algorithms, you may have to spend multiple millions of steps of like training steps in order to achieve some good quality of a policy, which means that million steps can be translated into dozens of hours of training and interacting with real patients, which is not very good for the safety reasons as well. However, they're pretty good for exploration, meaning that if you apply such an algorithm, at some point it will find an interesting policy or it will generate an interesting trajectory, which does accomplish the task, but in general, the success rate of such an algorithm can be fairly low. In this paper, we consider the following 5 problems, which are all simulated assistive learning tasks, assistive robotics tasks, which are assistive feeding, assistive scratch itch, assistive drinking, assistive bed bathing, and assistive arm manipulation. All are accomplished with a 6 degree of freedom robotic arm. The success rate is basically a metric. It's a well-known metric in imitation learning community, and in this case, it's fairly easy to demonstrate the quality of the algorithm using this metric because the reward here is not super obvious. The simulation is done using the assistive gym, a modified version, modified by us, which is a physical simulation, quite precise, maybe not visual, but visual fidelity, but the physical fidelity is very high. So if we just train a reinforcement learning policy, we get something like this. This is a success rate curve. And as an x-axis, you can see the number of training steps, and the scale is in millions. And on the y-axis, you can see the success rate, meaning that the percentage of successful episodes. So this is evaluated in the following way. We conduct 100 of evaluations, 100 trials, and how, I mean, we determine how many episodes of those of that 100 is successful, and then this rate is reported as a success rate. And as you can see, at first it's zero, of course, the task is not accomplished at all. But at some point, it becomes greater than zero, which means that there are some successful trajectories generated by this algorithm. It means that this algorithm is still very bad. It fails most of the time, but sometimes in those evaluation sessions, we can get some demonstrations, some successful trajectories. Maybe not diverse, but some. And still, as you can see, the reinforcement learning algorithm does not achieve very good scores in this task. This is a proximal policy optimization algorithm results, and as you can see, the success rate after 1,000,000 steps is about 14%, which is not very good, especially for a safety critical environment. But again, we can use it to collect some trajectories. So basically what we do is that when we see that some successful trajectories are generated during the evaluation, we start collecting them. We start basically collecting trajectories from the distribution induced by the policy that we've trained. And this policy changes during the training, and therefore the successful trajectories are also fairly diverse. So basically, during the just 800,000 steps, which is like half of the total amount here, we may collect about 500 to 1,000 diverse trajectories, which then can be used to train a imitation learning algorithm, i.e., in our case, we use the diffusion transformer policy. And this is basically also can be improved by looking at certain characteristics, such as the amount of force applied to a human, such as the speed of the velocity of an arm, the speed of operation, the number of time steps, and you can also filter the good trajectories, basically effectively trimming the distribution of a training data set. A little remark about the diffusion models. The diffusion models are deep diffusion models in this case are known to in the modern deep learning world as a very good instrument for a generation, as a generative model, for instance, for image generation. So how does it work? Basically, we take an image from a data set, in this case, from a data set of celebrities. Then we apply the noise to it in capital T steps, like multiple times, some Gaussian noise. And basically, this procedure comprises a process, which is a diffusion process, a reversible Markov chain. And what we can train then is a neural network which would approximate the inverse transform from xt capital to xt capital -1, from xt to xt -1, and so on to x naught. And so effectively what we do is we learn a neural network which denoises an image. And if, for instance, in the case of t-1, you can see an image of a human, and the denoising process, the following further denoising process is fairly simple from a human perspective. If we feed it then a fully just regenerated Gaussian noisy image, you can then basically generate a whole different picture of a person, which will be sampled from a distribution of a training set. And in the real world, in the modern world, you can be more familiar with such a model conditioned on text, meaning that this denoiser will be conditioned on a textual embedding, i.e. on a textual description of an image from a data set. And the distribution that it would learn to sample from, to generate images from, would be a distribution of images given text. So then this allows us to just set a text prompt, such as surrealist painting of a floating island with giant clock gears populated with mythical creatures, something like that, such a complicated description. And it would allow us to generate this high quality, high detailed, very interesting image. The same on the right, high fashion photography in an abandoned industrial warehouse with dramatic lighting and edgy outfits. The same. So we can use the progress made in this realm, in the realm of generative models, for imitation learning. And the way we do it is that instead of an image, we consider plans, i.e., vectors of actions, um, which are like A1, A2, AT of some short horizon, for example. And if we condition them on text in case of images, in this case, we can condition them on a set of observations, previous observations, such as states that we have seen, camera readings, etc., etc. And effectively, we learn to sample, basically generate action plans from this distribution, from distribution of potential plans given the observed states, observed observations, basically. This is a result of a diffusion policy, visual motor policy learning via diffusion, via action diffusion paper by Cheng et al. And we use the modified version of it in our policy. So if we just simply apply this idea to of training to the PPO algorithm, we obtain a super high scores in like in success rates, which are much higher than in case of a raw PPO, raw reinforcement learning algorithm. In this case, it's like 60% gain, 50% gain, 60+% gain, and so on and so on. Even in case of a task which is super complicated, such that PPO in millions of steps can only achieve 3.5 success rate, we can achieve more, 14%, basically proving that PPO can work as an exploration mechanism. And then, in order to apply visual signals here, we do the following thing. That was all for using the states, states which are privileged information, unavailable in reality. We can basically then, using the pre-trained model with the privileged data, using reinforcement learning, use the same approach to learn a division-based diffusion policy algorithm, which will be based only on images plus some odometry without any privileged data. And the neural network architecture would look something like this. We have odometry encoded by multi-layer perceptron. We have two image encoders from two cameras, which are encoded with separate convolutional neural network encoders. And all they are fed into the UNet denoiser from a diffusion model policy, which outputs an action plan. So this is a trajectory demonstration of a drinking task from left to right. Time goes from left to right. And as you can see, the cup is brought to a mouth quite smoothly, and as you can see, the trajectory is not super rapid. And again, this is all without even having to interact millions and millions of steps. So these are the results. As you can see, the vision-based diffusion policy is, of course, slightly degraded from the state-based diffusion policy because it does not have access to the to the privileged data, but still the gain is fairly high. The degradation is fairly marginal, but the gain is fairly high. Okay, this is it. Thank you for attention.
Thank you, Andrii.